When running electric current through hydrogen gas, the plasma doesn't emit a continuous rainbow of light. It fractures into defined, isolated bands of colored radiation. This discrete spectrum is governed by the Bohr-Hamiltonian, but a close analysis of the math reveals a redundancy. The system produces multiple wave functions that share the exact same energy level. Look at the n=2 energy level. Within this single tier, there are distinct orbital states, denoted by L, and magnetic states, denoted by M. Despite their different physical shapes and orientations, they possess identical energy. In quantum mechanics, this is called degeneracy. As physicist David Griffiths notes, degeneracy is rarely a coincidence. It is usually a direct product of physical symmetry. This leads to a specific analytical question. How does the rotational invariance of an atom mathematically force different quantum states to share the same energy? The attractive force between a proton and an electron is described by the Coulomb potential. This function depends on r, the radial distance between the particles, and ignores angular direction. Because force depends only on distance, the space is isotropic. We can freely rotate the coordinate axes, and the potential remains unchanged. Thus, the system possesses a symmetry. Its Hamiltonian is invariant under rotation, because the angular variables cancel out. The generators of these spatial rotations are the angular momentum operators. Because the space is isotropic, the Hamiltonian is immune to the action of these angular momentum operators. This provides the algebraic foundation for a proof of degeneracy. These commutation relations prove rotational invariance. The Hamiltonian commutes with both the total angular momentum squared and the z component of angular momentum. When operators commute pairwise, they represent compatible observables. We can know the properties associated with each one simultaneously. Compatibility allows us to find simultaneous eigenstates, wave functions that satisfy the eigenvalue equations for all three operators at once. Diagonalizing these operators generates a specific set of constants for the system. The Hamiltonian provides the principal quantum number n. Total angular momentum yields the orbital number L, and the z component provides the magnetic number m. The isotropic geometry of the atom has locked the system into a mathematical coordinate system. Every valid eigenstate is uniquely defined by a specific combination of n, L, and m. To find these states, we use separation of variables, splitting the wave function into a radial piece and an angular piece. Spherical harmonics are angular eigenstates. Varying m creates different spatial shapes. This is contradictory. The Hamiltonian is perfectly spherical, yet produces directional states like this vertical pz orbital. Rotated 90 degrees, it morphs into orthogonal x and y orbitals, losing its original z orientation. Symmetric Hamiltonians do not require symmetric states. In hydrogen, only the L=0 s orbitals possess spherical symmetry. However, the energy eigenvalue of this rotated unrecognizable state is identical to that of the original. Rotating a hydrogen eigenstate yields a different wave function, but the symmetry of the underlying Hamiltonian ensures that the energy level remains the same. We can prove this algebraically. The individual x, y, and z components of angular momentum do not commute with each other. These are the ladder operators, built from x and y components. Since the Hamiltonian commutes with them, we rewrite this as an equality. Applying both to a stationary state, their commutability lets us swap their order. Evaluating the Hamiltonian then yields the energy eigenvalue En. This grouped term represents a specific operation, a ladder operator acting on a state. This operation produces a new wave function proportional to a shifted magnetic state, where m has stepped up or down by 1. The new wave function, despite its different m value, is multiplied by the same energy coefficient En. For any given orbital shape, there are 2L plus 1 possible spatial orientations. Assuming a new orientation does not change the energy, because the universe is isotropic. There is a distinction between M degeneracy, which concerns orientation, and L degeneracy, which concerns differing shapes like 2S and 2P. Rotational invariance makes M degeneracy a requirement for every central potential. In contrast, L degeneracy is a mathematical quirk specific to the 1/r nature of the Coulomb potential. It is not a fundamental property of space itself. The physical symmetry of the potential forces the Hamiltonian to commute with angular momentum operators. That commutability allows for simultaneous eigenstates, labeled by n, l, and m. Finally, those non-commuting rotational operators ensure different spatial orientations exist at the same energy level. The quantum numbers n, l, and m are the inevitable products of the atom's rotational symmetry within an isotropic universe.